Welcome, everyone, to the Jones Seminar lecture series for today. So I'm Saul Diamond. I'm a professor here at Thayer, and I'm here to introduce our speaker. Our speaker is Dr. Kausiksankar Das, who's an associate professor of physics at the University of Maryland, Eastern Shore. And I want to share that before that, Dr. Das was a faculty member and research associate in the Department of Physics at University of Toronto, Canada. He earned his PhD at the Indian Association for the Cultivation of Science in India. And earlier this year, Dr. Das received the Regents Faculty Award, the highest honor presented by the University System of Maryland Board to exemplary faculty members. So we're honored to have you here today and sharing with us your presentation on fostering critical thinking and innovation, a design thinking approach.
Thank you so much for that nice introduction. So I guess I will use this PowerPoint slide. So is it automatically mirrored for the Zoom? Yeah, okay. Very good. So thank you everyone for inviting me to Thayer School, and especially Ian Baker. He is not here, but I know he's in Zoom. So he's joining us through Zoom. And today I'll talk about fostering critical thinking and innovation, design thinking approach. So first of all, yeah, sure, yeah, go ahead. And I may need your help when I'll switch back and forth. Yeah. Okay, great. Thank you so much. So first of all, I'll define what these things mean, individual terms, design thinking approach, and critical thinking and innovation. So we'll define each of the terms, and then we'll go into type, test, and refine, and implement the final solution that you get. But in each of the process, you involve the stakeholders. So that's by definition, you take the input from the stakeholders in design thinking. So another thing that design thinking actually focuses on is that most people don't make such of an effort to explore problem space before jumping into the solution phase, right? Solution space. So even before understanding the problem properly, we try to create solutions, and that creates problem. So here we are in academic environment, and we'll talk about design thinking in academics, where the problems are and how to solve those problems. First of all, identifying the problems. Could we fully understand what customers need? So design thinking centers the design process on human beings by understanding their needs first, right? And then include the stakeholders, include the customers, and throughout the development and the testing process. This is absolutely necessary that we do that. We include them in each step. So in the education system, how can we do that? So if I mirror that sentence here in education, that centers around the education process on our students and include the students throughout the development and testing process. So that's how you bring the design thinking ideas in education, right? So student-centric education system. Now, how do you naturally learn? pictures tell a tale, right? So this is a nice picture, and this is naturally a group of kids. They're learning naturally, and the natural learning is curiosity-driven. Whether it does not matter whether you are in the West or you are in the other part of the world, we are naturally curious. And we learn from observing, from discussing, by making groups, and we discuss things, we brainstorm about it, and this is a diverse group. Each diversification brings different perspective of understanding. And why does that not happen in our classroom? So we have to understand student psychologies, human psychologies, why this natural learning, this natural curiosity-driven discussion and brainstorming, why it is not happening in our classrooms, right? Let us talk about some psychology, human psychology. Forget about classroom. If I see this picture, if you are in front of an eating place, somewhere like this, if you don't understand a bit of the language, you know what it means. You know that you have to go to the front of the counter, you have to order your food, they will hand you the food, right? And you take it and go somewhere to eat. If you go here, it tells you that you go inside, somebody will come and take the order, you sit there, and the food will be served to you. It's inherent, it's there in the architecture, it's the ambience. So if we see this classroom, what is the ambience what does it tell you? Just like this, somebody will talk in front of you and you will take notes. It's not conducive to the natural discussion, it's not conducive to the vigorous brainstorming, isn't it? So it's in there, inherent in the architecture, in the ambience. So this is what we are doing now. And this is what most of the classrooms do. And then if we say that why is not education, the classroom teaching is not so interesting for the students, it's inherently there. We don't do that in pubs or in coffee shop, in restaurants. We express ourselves, we debate, we brainstorm, we fight for so that our opinion stands out, right? So why don't we do that in a classroom just like what we do here or here? So let us take these lessons and bring to the classroom. If we can create that ambience conducive for group discussions, conducive for vigorous brainstorming and debates, and natural curiosity-driven learning, then we can get the same outcome, isn't it? It's natural to us. So this is one picture from Carleton University. I think several of the faculty members are there from Carleton. So I took this picture because this is what we call like this curiosity-driven group discussion-based learning, where students are engaged in every step of the learning process inherently. And when they're given a problem, they take the problem, they discuss with the group, they come up with a solution, they debate on it, and then you learn naturally. What is the role of the faculty members here? Role of the faculty member here is more of a facilitator, not an instructor. You don't instruct the students to do this, right? Rather, it's more of a bottom-up approach. You give an open-ended question and let the students decide what is right, what is wrong. You are a facilitator. You guide them to the right answer, not give them the right answer, right? So it is sort of guided discovery for the students. And that learning obviously is more natural. And I tried this in my previous institution at University of Toronto. So we created some new practical rooms based on this philosophy. And you see the first line of that, the first thing you notice when you walk into one of the new physics practical rooms is the hum. And that hum is so important for natural learning and to bring that excitement of learning. And this became a flagship program at University of Toronto. We grouped the students and we grouped them together. We used clicker questions to bring out vigorous discussions. And let me give you some examples of those clicker questions. Before going into that, let us start to define critical thinking. So group discussion is not the only thing that we need. Group discussion plus critical thinking that we need for a successful learning outcome. So what is critical thinking? Critical thinking is the ability to understand, apply, analyze, evaluate facts or principles. And without critical thinking, anyone? What does that mean? It means progression from ignorant certainty to intelligent confusion. And that is so true. You'll feel that. So if we don't realize, understand, and analyze facts, then it creates confusion, more confusion than the proper understanding. And I like this joke. What I don't understand is how they get cubic centimeters in round bottles. So if we talk about the philosophy of learning and the taxonomy of learning, it always starts here. It starts from remembering facts, and then you understand, then you apply those understanding, then you analyze, and then you evaluate based on your understanding and analysis, and then you create something new. So the title of the talk was about innovation, right? How you innovate more, you create an innovation ecosystem. So if you don't go up to that point, to the ladder, to the apex point, crossing all these steps, then it's almost impossible to create that proper innovation ecosystem. I mean, system, I'm talking about not one or two innovations. It's like where system produces innovation. So now we'll talk about some critical thinking question, and for that I would suggest you take out your cell phone and go to this website. It's called www.menti.com and enter this code 70783684, or you can use this QR code. And I will now switch to Menti, to the other one. So I guess I'll use the Alt tab. No. Yeah, I'll go to, I have the quiz.
You stop share and then reshare with the vendor.
Oh, okay. Stop share.
And then share again.
And,
Share screen at the bottom.
oh, okay, share again.
Choose the Menti screen, whatever your...
Yeah, okay. Okay, so this is, now I'll show you again the code. Don't worry.
Okay. So yeah.
Show voting instruction. Here you go. Quiz, it's not started yet, so I'll
I'm able to enter my name.
yeah, so you can use any name. You don't have to use your real name also. Don't worry about the names. Nobody would know who is giving correct answer, who is giving wrong answer. So don't worry about that. So I would like everyone to participate, and we'll just do a survey. Okay? Okay, everyone is in? So let us start the first question. And Oops, it started from a wrong one. But anyway, so let us start this question. So everyone, how many of you know this Newton's second law? And this question is about a Newton's second law question that I use in my undergraduate physics class. It says Steph is reeling a fish steadily upward and at a constant speed. And the question is, what is the force, upward force, in comparison to the downward force? Is it greater than the downward force? Is it equal to the downward force? Is it less than the downward force? It is greater than the downward force, but there is no upward force. Good, so there is 31 participants. Time's up. Okay, good. So it's 23 and 9, 5, 9, 10, 15. So 23, 15. So 2/3, 1/3. So that's the distribution. So, and I guess most of us know Newton's laws, Newton's second law. Let us go to the second question. So why, let me explain it why. So you know, the tension force, there are two forces acting on the fish. One is tension upward and weight in the downward direction. What does Newton's second law say? Newton's second law says that net force acting on the fish is equal to mass times acceleration. But the fish is moving upward at a constant speed. So the mass times acceleration is 0. So tension has to be equal to the weight, right? And this is a conflict between your common sense and the physics sense. Common sense tells us that, yeah, if something is moving, there has to be a force in that direction. But Newton came and said that no, it is not true. It's not just moving, it has to be accelerating. We know that. We have learned that in class. So let us look at this question. Bianca is sitting on a pickup truck. The truck is accelerating to the right. In what direction does the friction force act on Bianca? "23, 24, come on. You are free to discuss with your nearest neighbors. Time's up. Wow, look at that. 25-16. So, what's going on? I mean, why is that so? Why this the friction is in the direction of the truck? Let us look at that. Again, Newton's second law. I'm just using Newton's second law, nothing else. So what does Newton's second law say? That net force acting on Bianca. Bianca is the point particle here, right? Bianca, or the net force on Bianca is mass times acceleration. Mass of Bianca times the acceleration of Bianca. Now you are standing by the side of the road. You are looking at Bianca. What is Bianca's acceleration? The same acceleration as the truck's, right? And what is providing that force? That's the only force. There is only one force acting on Bianca. That's friction. So it breaks that, there's misconception that friction, we often say that friction is opposite to the direction of motion. Direction of which motion? Right? So these concept cartoon questions we created with one of my colleagues and collaborators, Larry Gornick, who gave a talk here also in maths department. I know he's a great cartoonist, and we are creating these hundreds of questions, cartoon clicker questions, to talk about these concepts. This is another friction question. A car is driving up a hill at constant speed. Which arrow shows the direction of frictional force on the car's tires? Let's see. I know you can do it. And discussion, that's the key thing. So from 2/3 of the class giving wrong answer to discuss it with your peers. Okay, 3, 2, 1, boom. Okay, it's better, but still, we are still not there. So we had to go back and learn Newton's second law again, because there is so much misconception sitting there. It's like for instructors, sometimes it becomes very puzzling. Why are we wrong? Or for the students also, why are we making mistakes? Because the perspective, how we learn and how we look at the problem. So here is the solution. Net force is equal to 0 because the car is driving up the hill at a constant speed. The other force acting on the car is mg sine theta in the downward direction, right? And obviously, the friction force has to be there to balance it so that the net force in that direction is 0. It has to be. So this is where our education fails. This is to show. This is not like to show where why we make mistakes, but or you learn more, I know more. Not like that. But now, we'll go into a different regime. We'll go into the circular motion. And I love this joke. So this is a Bond joke. It says that, how do you like my centrifuge, Mr. Bond? When I throw this lever, you will feel centrifugal force crush every bone of your body. You mean centripetal force? There is no such thing as centrifugal force. It's a laughable claim, Mr. Bond. And then he says that you have to do a coordinate transformation to get the centrifugal force. And he said, Bond says, come on, you do really want me to coordinate substitution in my head whilst here? He said, no, Mr. Bond, I expect you to die. I don't expect any student to die because of these questions. So let's go to the next question. So it's an alien. The alien, teeny aliens land on their craft near the outside edge of the record turntable. And the turntable is rotating at constant angular speed. In what direction does the friction act? It's a Bond question. Do you want me to die? No. I want you to answer. So let's see. Again, discussion between students, and you can do it. Okay, much better. So see, discussions really, they improve. So much better, but still not perfect. So 18 and not so good actually. So I just looked at the relative strength, but it's not so good. But still, again, if we look at the problem from this perspective, just now we talked about this Bond joke. And in a rotating frame, if you look at it from outside, what is the direction of force or acceleration? Towards the center. Everybody, we have learned that in our Physics 1 classroom. So that's the direction of acceleration. And Newton's second law says that whatever the direction of acceleration is, that would be the direction of net force. What is the net force acting on that alien? Only friction, and there is nothing else on that tiny small aircraft. So friction is the force which is creating that acceleration. So we have to always think from the other way around. That's what I teach in physics classroom now, that check the acceleration first and then comment about the forces. If we don't do it, then we are prone to mistakes. And this is what is happening here. Most of us are trying to find forces first and then trying to relate it to the acceleration. It should be the other way around. Check what is the direction of acceleration and then what is creating that acceleration. And it's not just here, it's everywhere. The confusion is there. And the confusion was there for thousands of years before Newton came. Like big philosophers and educators like Aristotle, big brains like him also made the same mistake. So it's okay to make mistakes, but we need to understand where the mistakes are happening. So problem space, going back to the design thinking, where the problem is, where is the problem, real problem in understanding, before throwing solutions. So let us do this, let us do different techniques in pedagogy. We have to understand where the problem is. Okay. So next question, we have 2 more questions left, so let us look at that. This is conservation of energy principle question. I gave the hint. So a car starting at rest comes down these ramps, which are all the same height. Which car will have the highest speed when it reaches the ground? Ignore friction. Discussions? Okay. Very good. Wonderful. Now we are getting there. Very good. So 31. So, and what's going on here? So this is, everybody now understands that this is conservation of mechanical energy. The total energy at the top is mgh, only the potential energy is there. Total energy at the bottom, because there is no frictional loss, is just half mv square. Conservation of energy tells us that v equal to square root of 2gh. H is the same, and so the speed will be the same for all the cars. And then we do the last follow-up question of that. And this is festive season coming, so you are getting these gifts from your nearest and dearest ones. One is small gift, one is large gift. So same slope. Now, which car will have the greater speed on the ground? There is no friction. Okay, let us see. See, this is what I wanted to demonstrate. In the previous slide, I showed that V is equal to square root of 2gh. There is no mass involved in the solution. Even after that, 9 plus 3, 12 students in this class, 12, wrong answer. Yes? So no, I don't blame you. So this is I'm talking about the psychology of learning, right? So we assume, as instructors, we assume that this is obvious, that I have showed everything. Students should learn. But that's the conflict zone between our common sense and the physics sense. Newton's laws, we learn, we get A grade, we can solve all the problems, but when we try to connect it to real life problem, we don't use it. We go back to our common sense. So this is the problem. This is where the problem lies. Okay, so let us go back to our original slides, and I would stop share, and then I will go back to my slides, and then what should I do? Should I share again? Yeah, please help me. And
You'll bring the slides for the rest of the time?
Okay, yeah. Okay, good. Wonderful. Yeah, I got it. Yeah, so we did that. So now let us go back to the Bloom's taxonomy. And this demonstration, what we did today so far, it tells you that we assume that we have learned Newton's second law and conservation of energy principle. We understand it. But we are still stuck. Majority of us, many of us are still stuck here. Remember and understand. We are not applying. How on earth we will analyze it, evaluate it, and create it, right? So that's the big gap, right? So it starts from the classroom. It starts from the classroom that you encourage students to discuss. You encourage students to do this critical learning exercise, to do more critical learning exercise. But it's not all. Our goal is to reach there, from here. So we have a long way to go. So what else we can do? So when I show this problem in my class, and we have explained that this is tension is equal to the weight, some honest students every semester, they tell me, Dr. Das, I don't believe you. And I say, thank you. That's an honest statement. And this is where the real learning starts. Because many of us don't say that, but we don't believe that, because we still believe in our common sense. So what I tell them? That construct your own experiment to test what your hypothesis, what is true. So how do you construct that experiment? You take a force sensor, you take a pulley, I give them all these components, and then a constant speed cart, and there is a mass which represents the fish, and that pulley, that cart pulls that fish at a constant speed and check what the value of the force sensor is giving you. Is it equal to the weight of the mass or not, of the fish or not? If it is equal to the weight of the fish, then this Newton's law is correct. If not, then there is a chance that your common sense is correct. That's the hands-on active learning part. It's not like creating some predetermined labs and give the students to do hands-on active learning. Here there is a conflict, so you know that there is a conflict. You have understood where the conflict zone is. Create the labs according to those conflicts, so that students get their queries, their misconceptions clarified by doing this experiment. Or this question: if when I don't give the hints, there is a similar distribution. If I don't say that use the conservation of energy principle, there is similar distribution. And then they say, I don't believe you, that all the cars will come down at the same speed. Well, you create your own experiment using the Hot Wheels. We have a bunch of Hot Wheels and the sensors, and create your own experiment, test it. So that's the testing phase, the hands-on active learning phase. We create several of the labs according to this, which are like synchronized to those questions, critical thinking questions, and labs are built based on those. Okay. The third part is the authentic discovery labs. So once the students go through these processes, the critical thinking exercise and corresponding hands-on lab, then we create some very immersive hands-on active learning labs for them. And actually, after that, we created like 2 courses, like your capstone courses, like 89 and 90 here, I believe. So our is 498 and 499 level courses. So there, we bring students from diverse background. Diverse background means not just diverse background in terms of ethnicity or their origin. It means that from diverse disciplines. One student from chemistry, one student from physics, one student from mathematics, one from engineering. We form a group and give them one project. The diversity of thought process is very important. So the same problem, different students look at differently, and they bring different perspectives on the table. And that creates wonders. That makes the project so vibrant, and great things can come out of that, right? So we do interdisciplinary research where all the components are there of biology, chemistry, physics, like that. My goal as a supervisor is to create those modular research projects from cutting-edge research. I do that personally, and I love to do that. I read all these current research papers, and then I try to create modular research projects which are doable by undergraduate students. My research is with undergraduate students. I try to do this research with undergraduate students. And the success of this project, of this approach, depends on how well you can do this modular research projects, so that these are doable by undergrads, but can give you great results, because these are very cutting edge research projects. So, and final research project can be presented at a national meeting or published in a scientific journal, and or may lead to new research. That's where the curiosity-driven path goes on. So you start with something, and then you end up somewhere else. And the beauty of working with undergrad students is that you can do a lot of risky projects, so-called risky projects, where there is no guarantee of success. So with grad students or postdoc researchers, you have to have a safety net, because their careers depend on that. But if we start early and train these undergrad students for doing like proper research, authentic research, you are not only, you can take risks, because if we are successful in the project, it could be big. If we fail, it's not a failure, because the students are going through that research process. It's a valuable learning experience for them. So it's a win-win situation. So we can create this trained pipeline of students to go to grad school. Right, that's the goal. So one of those projects was like this, that organic solar cell. We started working on some colored fruits and berries. Those are edible and taste good, but it works very well as a solar cell, because those dark pigments, or anthocyanin, is very light active material. So you can use those light active anthocyanin to create your solar cell. Its efficiency is not very high, but it shows all the properties of a solar cell, and the students learn how to characterize a solar cell, all the steps. So we did it. So this is the solar cell, and this is actually these are called dye-sensitized solar cell, DSSC. Sometimes it is called Grätzel cell. So Grätzel was pioneering physicist who developed that technique. So we did that. We created these solar cells. We characterized it. We measured the form factor, the efficiency, and everything. And we created a report. We presented this work in AAPT meeting, and then I got a call from Williamson Mary, one professor, physics professor. Can we include that in our capstone research? I said yes, but that's not the story that I want to convey. That's what happens is that in creating that solar cell, we need to use this semiconductor, is titanium dioxide, right? And there is a very similar semiconductor, it is zinc oxide. So we got curious that similar band gap, similar structures, everything similar. So if we replace titanium dioxide by zinc oxide, will it still work? And surprisingly, it didn't work at all. And we started investigating what is going on, where from this error is coming, whether it is an error or not. And that's the curiosity-driven path. And we started investigating it, and eventually we discovered that there is a resisting switching memristive behavior in light-activated adsorbed zinc oxide thin films. And we published this paper. This is an undergrad student at that time, Ben Burns, and it became one of the top 100 read articles in scientific reports. So for an undergrad research article, that was very big for us, right? So this is curiosity-driven research led us to that. Now, the story does not end here. Surface gets modified, and then if it changes its characters, you can say that it's a surface effect. If not, you say it's a bulk effect. So that was the argument at that time. But we didn't have a plasma chamber at that time in our lab. So we thought, let's create plasma in the lab. And what is plasma? Plasma is the fourth state of matter. Plasma is ubiquitous. It's in the sun. It's in lightning. It's in fire, neon lamp, auroras, interstellar gas. You name it. Plasma is everywhere. And not only that, plasma has thousands of applications. So starting from medical applications to rocket thrusters and astrophysical things, fusion research, tokamak. You name it, it's everywhere. So I had a discussion with my undergrad students. Guys, can you make some plasma in our lab? We need it. And total disappearance for 2 weeks. And these guys are brilliant. They came back. Where is that? They came back with this. They said that we created corona discharge plasma. And they have chosen this Corona bottle, and there is light written in there. So Dr. Das, this is Corona light. And this is plasma. Yes, this is plasma. Fantastic. But it will not serve our purpose. So we cannot, this is not like, we cannot treat our substrate with that. So this is a nice project. And then they said, when this pandemic era, they came back and said, can we use that corona discharge to treat corona in a corona bottle? Coronavirus. That's a nice idea. Actually, the plasma is used now to destroy coronavirus or many viruses. So that's another application of corona discharge in a corona bottle to treat coronavirus. Anyways, so let us go back to plasma. What is plasma? Plasma is a soup of ions, and plasma is the fourth state of matter. So most of us know that, but why do we call it fourth state of matter? Anybody? Any idea? You have heard this term, right? Fourth state of matter. So basically what happens, if you take a solid state of matter, to make it a liquid state for the phase transition, what do you need? You need energy, heat, right? For the second state, liquid to gas, you need more energy. Now, if you have a gaseous state, if you put more energy, if you keep on adding energy, what will happen? Eventually, the electrons will come out of the outer shells. And then it would create a soup of ions, positive and negative ions. There will be recombination and the separation also. But if it reaches a steady state, then if you keep on supplying energy, then that's the fourth state. It's a soup of ions. So this is how normally plasma is created. It's two plates, electrically conducting plates, and you create a very high electrical voltage difference between them. And eventually there is a breakdown of the atoms and molecules in between, the gas molecules. And these whenever there is the separated electrons, they would start to accelerate in the direction of the electric field, and the negative ions will start to accelerate in the opposite direction. Again, Newton's second law, like force field is equal to force per unit charge. So force will create acceleration, and then they would bombard with other molecules, and then they will create secondary electrons, and they will bombard tertiary atoms, and this is how it will be a cascade of atoms and ions. Right? That's the normal plasma creation mechanism. So first of all, you have to add energy to the system in the form of heat or electric field in this case. And this is a characteristic plasma curve that shows that plasma creates normally in an electrical field at a sweet spot, and this is called Paschen curve, P-A-S-C-H-E-N, Paschen curve, right? So that's the normal way to create plasma. So we thought, instead of that electric field, why don't we use microwave? Microwave also gives you energy, right? It supplies energy. That's how your cup of water gets heated up, right? So if you add a cup of water in a microwave, what happens? That microwave is oscillating electromagnetic wave. I mean, there is oscillating electric field and magnetic field also. So oscillating electric field oscillates the water molecules because it's a polar molecule. Water is a polar molecule, and they bump with each other, and that energy is converted into heat, right? And that's how it gets heated up. So if there is no polar molecule in there, there will be no microwave heating, right? So now, one of my students, Ben, so he tried that. He created that environment in that jar from that understanding that he just put that substrate in there. He created some vacuum in there in the chamber using vacuum levels, and then he would put it in the microwave oven. It's a normal kitchen microwave oven, and then once it turns in, boom, there is plasma. Plasma was generated there. So, and it's reproducible. It's reproducible. We have treated our substrate with this plasma, and then that result got into that scientific reports paper. So it does, and there are many other applications we have used. So I'll come into that paper. I'll send all of you that paper also. So this is how that plasma was created. It's a water molecule. Even if you create vacuum in the chamber, there will be some stray water vapor molecules. However vacuum you create, there will be some stray water vapor molecules. So our hypothesis is that it's a polar molecule, so it will always try to align itself in the direction of the electric field. And if the electric field is oscillating, it will start to oscillate or it will start to rotate, right, if it overshoots, because if there is a phase difference. And we have calculated how much the energy, rotational energy can the water molecules gain from that microwave? Because microwave, you know the frequency and the power of the microwave. So from that you can calculate, and the moment of inertia of water molecules are known. So you can calculate that. And it's enormous amount of rotational energy it can generate. And it may happen that because of that centrifugal force, remember the Bond joke, that some electron may pop out. Yeah? That creates the primary electron source. I'm not saying that this is a theory that has been proven. This is just a hypothesis. If you challenge me, create your own experiment to disprove it. Okay, so that's how the curiosity-driven research goes, right? So that free electron then in that electric field collides with other molecules, then it creates that cascade, the same route, and then eventually you create plasma. And we tried with different flasks. Plasma in a 250 milliliter flask, plasma in a 125 millimeter flask, and it was there. We used several other containers everywhere. It was shown everywhere, and we sent this paper. We converted this paper into an education paper, so that people who don't have that funding, even in high school or in other parts of the world, they can use plasma and they can do all sort of cutting-edge research also, plasma treatment, by using plasma treatment. But the referee was not very convinced. He said it's impossible. And we went back and forth, and eventually the referee once said that, yes, it works, and he created his own lab, he created his own plasma. That's the best referee we have ever got. Okay, so it became, 5 minutes, right? So it became an instant sensation. MIT Technology Review featured our work, and they even went ahead and said that this technique opens the way for a new generation of experiment with this exotic form of matter and perhaps develop new applications. So this is an undergrad work. I don't know whether this will happen or not, but this is a nice compliment for undergrad work. It was published in American Journal of Physics. It became an editor's pick, and that was that. The story does not end there. See, this is like continuation of stories. The referee commented. We said that rotating water molecules like that may flip the water molecules back and forth because the water molecule's shape is like that. It's an asymmetric toy type water molecule, the shape. And the referee said that, on what ground are you commenting like that? We said, let us prove that. So we designed an experiment, zero gravity experiment. We created a payload, and we flew in one of the zero gravity flight from NRC, Canada. So and one of the students who was involved in that project is here, Ayobami. So he is now at here. So you see these rotating solid objects, asymmetric toy objects. These are this experiment is not done by us. This is in the International Space Station. Just look at that, the key handle, how it behaves. It's very interesting. So what we tried to show that water molecules, here we created a toy water molecule here, and we rotated it, and we wanted to see if this water molecule shows that flipping behavior in zero gravity that we commented in our paper. Look at that. Okay, so let me show you some more. So I should show this picture to embarrass you, Ayawami. Okay, so yes, look at that. So this is the water molecule. if it is below some critical angle, it will not do that flipping behavior, which is understandable from the numerical simulation also. And now look at that. This is what it behaves. So it is to show that one research takes you to different directions if it is a curiosity-driven research. And this is amazing. And students love it. I love it. And everybody loves it. Okay, so let me conclude here. I have so much to show. This is the recent work we are doing on radiative cooling materials. Well, I'll talk about that in next chance. And our students are working on that. And I wanted to conclude with this quote by Steve Jobs in his Stanford commencement speech. He said, "Stay hungry, stay focused." It's a great speech. I'd recommend all of you to listen, to Google that. Steve Jobs, Stanford commencement. And my lab's motto is, stay hungry, stay curious. Right? So this is some of our students' achievements. We got like cover page article. Our students got into Intel, NASA, Northrop Grumman, and so much so. And thanks to NSF and Department of Education for supporting our research. Thank you for your attention.